Hi guys, thank you for taking the time to watch the video and to take some notes so we can get a jump start on the next section. So our next topic is another technique to integrate, and it is, or a different type of integral to integrate, which is called an improper integral. And there are two types. And first, most of these problems do come on the multiple choice section of the AP exam, almost always, okay? It says there are two types. The first type is where at least one bound is infinity or negative infinity. So I gave you three examples showing one with positive, one with negative, and one with both. The one with both here at the end, the cosine x dx, it's kind of rare to see that, but we'll probably do one or two just so you can see how to work with it. For the second one, the next type of improper integral is where the function is undefined somewhere on the interval over which you're integrating it. So for example, there are three here. The integral from 1 to 5 of 1 over x minus 1, it's undefined at 1, and that's considered to be over the interval because 1 is a lower bound. The next one is the integral from negative 2 to 2 of 1 over x. That's undefined at 0. And the last one is tangent. Hopefully you recall that the tangent graph is undefined at pi over 2, which is contained in that interval. And I forgot my dx after. Oops. So I had put a star by this one because tangents and inverse tangents seem to be pretty popular on the AP exam. And knowing where the tangent graph is undefined is also pretty common to see on there. So let's take a look at the first type. And remember, you can pause this video if I'm going too fast. So we're going to integrate from pi to infinity sine x dx. So this is the first type of improper integral where one of the bounds is an infinity. So the first thing we're going to do is leave a little bit of space in front of the integral symbol, okay? We're going to integrate from pi to a. So we're going to replace the infinity with a letter, any letter that you want. And then what we're going to do after we integrate it is we're going to take the limit as a then approaches infinity. And I can tell you honestly, because I don't really like to lie to you, that if you forget the limit and you just integrate with the infinity, it doesn't change your answer. It's just this is the proper technique by which you should integrate. So if I was doing this in a multiple choice question, I would never waste time writing the word limit. I would just write it with an infinity as the upper bound, integrate and substitute, and then get my answer. But I'm teaching you the proper way so that in case this would show up on a free response, plus just so you know the proper technique, that you would get it right. So now we integrate like normal. And if you remember back in your limit days, you only drop your limit symbol or your limit notation once you've substituted in the infinity. So if we integrate sine, we get negative cosine x. And we're going to evaluate that from pi to a. And I don't really like having negatives in front, so I'm just going to kind of factor it out and just substitute in my upper bound cosine a minus my lower bound cosine pi. And now I'm going to let a go to infinity. So I have the negative of the quantity cosine of infinity minus the cosine of pi, which is negative 1. So it's going to become plus 1. So the cosine of infinity, you should recall that the cosine graph oscillates between negative 1 and 1 the entire length of the curve, which it never ends. So in order to find the cosine of infinity, well, you'd be a genius if you could figure it out, because you can't. It's undefined because it doesn't stop oscillating. So in this case, the answer would be non-existent or does not exist. And what we would actually say is that the integral diverges. Things can either diverge or converge. So when I can't pinpoint an answer, or if an answer goes up to infinity or down to negative infinity, it would diverge, even if the answer would be infinity. I can't put a quantity on it, so it's not finite. So that would diverge. Okay. Another example with the infinities is integrating from negative infinity to negative 1 over x squared dx. And again, we will replace our bound, our lower bound, with some letter. I'll just use a again. You can use whatever you want. And I'm going to bring up the exponent to make it a negative so that I can integrate with my power rule. And again, we don't drop the limit notation until we've substituted in the negative infinity. So this integral would be x to the negative 1 over negative 1, which I'm going to just rewrite like that. So x to the negative 1 over negative 1, which would be negative 1 over x. I'm going to substitute in my upper and lower bound. And again, I factored out the negative. Sometimes I do, sometimes I don't. Most of the time I do, so that I don't have all these negatives floating around everywhere. So I just factored that out and then substituted. Now I'm going to let my limit, or my a, approach infinity, negative. And yes, this will become positive. But 1 over either infinity will approach 0. So that means the answer to this limit is a negative 1. And since we were able to get a finite answer, this integral, we would say, converges. The answer to our integral would be negative 1, but again, we would say that that integral converges. And remember, an integral is the net area underneath a curve. Let's take a look at just one example of the second type, and we'll practice more together in class. We're going to integrate 1 over x minus 2 over the interval 2 to the 5. And if you notice, 2 is a point of discontinuity. It's where this graph or this function would be undefined. So we're still going to use the technique of replacing this bound with a letter. Not going to change. And we're still going to say the limit as a approaches 2, but I'm going to put something after that 2. And I'm going to go over here, and I'm going to, just on a number line, see if you can follow this on video. I want to integrate that function. Who cares what it looks like, really? But I want to integrate it over the interval 2 to 5. So when we talk about limits, we can talk about approaching a number from the left or from the right. We didn't talk about that with the infinities because you can't approach an infinity from the left or the right. You just approach it. But when I have a number like 2, we first know that we always use direct substitution with limits. But sometimes that doesn't work, so we have to approach from the left and or the right, depending on the problem. So if you're on a bounded interval from 2 to 5, so you're not really caring about anything that happens outside of that interval, then hopefully you can tell that if we had a choice by which to approach 2, we would approach 2 from the right-hand side. Slightly bigger numbers than 2, because the interval starts at 2, goes to 5. So I could only approach 2 from the right-hand side. So if you recall, that means we put a little plus up top. And now we integrate. And the integral of 1 over x minus 2 is the natural log of the absolute value of x minus 2. And we're going to evaluate that from a to 5. Let's substitute in. When I substitute in 5, I get the natural log of 3, so I can drop the bars, minus the natural log of the absolute value of a minus 2. Well, the natural log of 3 is the natural log of 3. I can't do anything with that. Now, we use direct substitution always. We always try that first, even if it says from the left to the right. But the bad thing is when you do use direct substitution and you just substitute in 2, you get the natural log of 0, which, if you know the natural log graph, which I cross my fingers and I hope you do, it looks like this. And there's an asymptote at x equals 0. So I can't actually find the natural log of 0 or any log of 0. So I have a little bit of a problem. So now is when we would say back in calc last year, let's approach this 2 from the right-hand side. So we're still approaching 2, but very, very close to 2 on the right-hand side. So maybe that is like 2.001. Very close to 2, but from the right-hand side of 2. And remember, when we approximate or when we find a limit and we're coming from a certain side, we want to get closer and closer to that number. So as the number inside here gets closer to 2, that decimal on the inside is approaching what number? Hopefully you're thinking 0, because the closer this decimal here gets to 2, the closer their subtraction or their difference would approach 0, because this would be 5 zeros and a 1. So then, in order to answer this, we have to think of the natural log graph. So again, this decimal will keep getting closer and closer to 0 as the decimal we substitute in gets closer and closer to 2. And as this graph gets closer and closer to 0, what's happening to the y values? Well, hopefully you see they're approaching negative infinity. So we'll have natural log of 3 minus negative infinity, which would become natural log of 3 plus infinity, which would just be infinity. Now, since infinity is not a finite answer, even though we get the answer of infinity, we would say that this integral diverges, because it's not a finite answer. So we get the answer of infinity, but the integral itself would diverge. And just to give you a graphic picture of what this would look like, 1 over x minus 2 is a rational function with a vertical asymptote at 2. And this says, I want to find the area underneath the curve from 2 to 5. That's what we were finding. So that's from here to here. Well, the graph part of it looks like this, the part we would be interested in. So if you're finding the area from 2 to 5, you want to find this area, but if you think about it, this graph is never stopping. It's going up, 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 up. So that area will never stop either. So in that case, our integral diverges, and that would be the conceptual or the graphical interpretation of what we just found. So the answer would be infinity, and the integral diverges. And again, we're going to practice this all period on Thursday and some of Friday if you need it. Thank you.